Hello, everyone. Welcome back to the AAS YouTube channel. And this is going down the education series. And I am super happy to have Dan Reichart with us today. Hey, Dan.
Hey, how are you?
I'm doing very awesome on this 21st of September, 2022 as we shoot this. And let's see, I'm in Phoenix. In Phoenix, we're still pretty warm. We'll stay warm until October-ish. But some of the humidity is going away as it moves back to the Gulf of Mexico, whence it came, and so we'll dry out here over the next couple of weeks.
Is today the official day, autumnal equinox, or was it yesterday? I can't keep track.
It officially is today. This is 21st.
Officially today. Sometimes it's on the 20th. It varies.
Yeah, it depends what time zone you're into. So
Oh yeah.
But there is an exact moment, in UTC.
Well, happy fall.
Yeah, happy fall. Yeah. So Chapel Hill. You guys still have the summer moisture? Have you leaves starting to turn? Are you starting to make the turn into autumn, fall?
I'm looking out my window and one tree, the leaves are beginning to turn, but it's still crazy humid here and hot. We had a brief reprieve, but it's back to summer for a little while.
Okay.
At least where I am. I actually haven't been on campus on and off since before the pandemic. My last class I taught in person was fall 2019. I did teach one online section.
Okay.
But after the pandemic, I had a year of leave to develop some of the educational stuff I'll be showing today.
Yep, cool.
And I don't go back till spring of 2023, so it's a huge gap.
Wow. Has the semester actually started at UNC?
It has started, yeah. Okay. Yeah. I still run the labs. I just don't go in most of the time. I have TAs that teach them.
Yeah, I actually haven't been in a physical classroom in that setting in about a decade.
Oh wow, okay, you have me beat.
I've been teaching online since about 2009 or so. And so all of it takes place that way. So it's always a challenge to do the labs, which is what we'll talk about today. How you do labs, how you do quantitative stuff, this kind of stuff. So it comes with its own challenges. But
I'm kind of anxious about my return because they're putting me in one of these cutting edge classrooms that they don't have. It doesn't have a center. It doesn't have a front, right? You stand in the center.
Yeah.
Going in circles, facing everyone. And with
screens
on all the walls.
Flip the classroom, right? And that's the motif. Flip it.
Yeah.
So yeah, very cool.
It should be interesting.
Well, it'll be a lot of fun. Very good. So let's talk about some of those educational things that you have been developing and what the target audience for those is and how other educators can make use of all that kind of stuff. So go ahead and take us away.
Sure. So I run a global network of telescopes called Skynet.
Okay.
We're on, let's see, Chile, Australia, Canada, the US.
Okay.
We're not quite as big as Las Cumbres. We're Las Cumbres without the money, let's say. Though in fairness, I must be fair, we've gotten a lot of funding from the National Science Foundation over the years. And recently from the Department of Defense. And not for what you may think. You may think they want to track satellites or something like that, but they are genuinely interested in astronomy education. It kind of surprised me. DoD wants a STEM educated workforce, and 10% of undergrads go through Astro 101. And so we made the case. And anyway, we have a lot of funding right now. $2 million from NSF and $3 million from DoD for education efforts.
Very nice.
Anyway, so it's a global network. Go ahead. You're going to ask a question.
I was just going to say, the Navy still as backup. We all use GPS these days, but as backup to be able to navigate from the stars as people used to do. So I can understand from that point of view. To have people knowledgeable about the night sky and astronomy education is actually in their benefit.
One of my formative experiences to become an astronomer was a Navy Pulsar search at Green Bank Observatory. I was there as a high school student using their teaching and training 40-foot telescope.
Cool.
And not that we discovered something, it was just a radio interference blip, but it's a transit scope, so I couldn't check for 24 hours. And so we're talking about it over lunch, and they overheard, and they shut down the Navy Pulsar search and let us use one of the bigger telescopes.
Oh, very cool. Oh, yeah.
In case it was a supernova or something.
You got an anomaly, we should look.
Yeah. And so, yeah. And so, it's a global network. We have telescopes that we have put out there ourselves. The primary site is Cerro Tololo. We have 7 or 8 telescopes there. And we vacated one of the domes for the Everyscope experiment, which some people may know about. Pretty cool experiment, a colleague of mine here at UNC Chapel Hill, Nick Law.
Yep.
And we have 3 sites across Australia. Some are in repair, in post-pandemic maintenance, but by the end of the year, we'll be at fully functioning there. We have a couple in Canada. And then we have partnered telescopes all across the US and also Canada and Australia. People come to us saying, hey, we have a remote system. Can we, remotely controlled telescope, can we put it on your system?
Yeah.
So they like our scheduling interface, our data retrieval, and all the tools that we've built for analysis, particularly for students. And
is the main purpose, or is it a dual purpose for these telescopes, for research and education, or are they strictly education, or how does that?
I'm glad you asked that. We are a 50-50 dual purpose.
Nice.
We built them originally for gamma ray burst follow-up. Trying to find the most distant explosion. A prediction I made with my grad advisor, Don Lamb, back in 2000. And then very ballsy me, I said, I'm going to go build the instrument to find it, even though I'm a total klutz in the lab. But we somehow pulled the first telescopes together and discovered the most distant explosion.
That is awesome.
A year later, in 2005, and held the record for 3 years. After that, I had the funding. I could hire people who actually knew what they were doing. And so we've grown. And now the network's used by professionals. We publish, we being someone somewhere publishes Skynet data in peer-reviewed journals once every 20 days.
Okay.
Everything imaginable, supernovae, solar system stuff. So we're very much a research network. But I very much value education. And when it's not being used by researchers, these are small telescopes, 16-inch to 32-inch typically. And we've created opportunities for students. And over the years, there have been many educational programs, many of them NSF funded. And I think we've served about 45,000 students that I know of. And I can't keep track of what everyone's doing across the network.
45,000 now, it's crazy.
Yeah, it's a great number.
So do students, or can an instructor who's leading a group of students, do they apply for time and then they get it, and then it comes at a certain day, or whenever there's a gap in the schedule, they get their images shot, or how does that work?
So it's a fully dynamic queue scheduled system. Okay. So you put in your observations whenever, and we have smart algorithms that juggle, when it's best observable, but also this telescope is 40% owned by this group, 50% by this. They have the TO rights, they don't. And so it can get complicated, but from a student's perspective, you just put it in. And if you're lucky, it comes back right away, but usually comes back within a day or two.
Okay.
Particularly if you select many scopes, right? If you select one scope and it's rainy there for a week, you're in trouble. But the advantage of a global network is it's clear somewhere, sometime.
Nice.
And people do in different modes. Some people purchase a chunk of time and do their own thing, and that's great. That's partially how we pay the bills. And some people use the Our Place in Space curriculum. It's one of the 2 undergrad curriculums I'm going to show you some stuff of.
Nice. Okay.
It's an Astro 101. So we have an Astro 101, Astro 102 curriculum. Okay. The 101 curriculum we've been working on since 2008. And so it's pretty developed, and we've partnered with Cengage Learning, WebAssign, which is owned by Cengage Learning. They're a homework assessment site that they also publish. And they charge a fee for it, but some of that money makes it back to fund the telescopes. It's a fraction of our operating expenses, but a lot of these efforts are born of enthusiasm and goodwill. And then when the initial grant runs out, they disappear. We've been doing this since 2008. So it's a sustainability model, and NSF actually appreciates it. So
very cool. Yeah, I use Cengage in my classes. I primarily use their they're basically their digital flashcards.
Okay.
to get across terminology or key concepts. And I have to say, students really like it. I mean, I'm always surprised that when the evaluations come back, how much they effuse over these Cengage digital flash mechanisms. And of course, they have a whole schedule, which is backed up by some neuroscience at some level to help you retain that information.
Right.
How quickly you need to be refreshed and all that kind of stuff. So I have a little bit of experience with Cengage there. So yeah.
They have a new thing called Cengage Unlimited. And so schools that use it, students are now signing up to this, and it's a base price and they gain access to everything.
Got it.
So if you have Cengage Unlimited students, they can try this stuff for free.
Yeah. Okay. I will check that out. I don't know exactly what Arizona State has, but I will look into it. Very cool. Very cool. So should we take a look at some of the stuff that's in the Astro 101? Or
yeah, so we have these two curricula. The Astro 101 curriculum. It's called Our Place in Space. It's meant for the giant survey courses, though we have small schools, community colleges, high schools, research ones, HBCUs, everything, rural focused, all girls, everything you can imagine using it. And so it's a little different than the second. Maybe I describe the difference first, and we can then dive into one of the more interesting examples, perhaps.
Cool.
So the 101 one is designed to scale to a national level. So it's a lot of short exposures, lots of planets.
Right.
When we're doing deeper things, it's short curated lists. The way Skynet works, if we have multiple things at the top of the queue that's identical, we observe it once and then distribute it to everyone.
Makes
So
sense.
this is really designed carefully to scale. It's single exposures, no stacking, no color. The radio work, and there is some radio work, because I believe in that firmly, is spectra, not mapping.
Okay.
But second curriculum, the idea is if they come back, then the second, there are fewer of them, so we can give them more telescope time. We can do color combination, and we can do radio mapping. And so the second curriculum is 50% optical radio. We're integrating a whole network of radio telescopes up to 30 meters in size for educational use.
Cool.
We've negotiated small fractions of the time on each. And and so it's called, the first one's Our Place in Space, Opus. It's the greatest hits the past 400 years, the cosmic distance ladder, great debate of 1920, the things that you teach in Astro 101. Right, normally in Astro 101, you have labs. They go out and use small telescopes and planetarium. That could be good and can be bad, depending on the experience, but it doesn't really connect strongly with the greatest hits the past 400 years, which is what you're teaching.
Fair enough.
You're able to do that. The second curriculum is for those who come back, and it's more about stars, galaxies. It's next level interpretation of color and non-thermal mechanisms.
There we go. Okay.
Yeah. So that's a breakdown.
Cool.
So what do you want first? Some 101 or some 102?
Oh, let's start with 101.
Let's start with 101.
Start off from the beginning.
Okay, so we'll share, and I'll show you some simple things that the large surveys. Oh, host disabled participant screen sharing. You got to let me.
Got it now. Go.
Okay, and let's see here. I'll show you some simple things. Of course, right now I have up one of the final things from the second curriculum, really sexy stuff. But let's start with simple things like in their first lab, they just kind of go crazy. We save the science for the later labs. The first lab's how to use Skynet, how to use Afterglow. Afterglow is the online image, web-based, student-level reduction package directly tied into the Skynet database. They don't have to acquire their data, download it, upload it, though you can if you're using another system as well.
Sure.
Something simple. So in the first lab, they're hitting planets. So let's bring up some planetary images.
Yay.
Let's do this one here. And so they get something like this back. So we teach them things like brightness and contrast control, where they can change the brightness and contrast, tweak it, bring out moons. They do lunar identification. They learn how to measure things like distances between the planets and the moons. We have like little plotting tools, measuring tools in here. There's a later lab where they will track moons going around a gas giant for a couple weeks and determine the orbit We
Right.
provide little applications where they can plot their distance versus time and Chi by eye model the orbit, get the semi-major axis, the period, and figure out the mass of the central body, Kepler's third experience. But here's kind of just a fun thing. I'll just do a quick color combination, which is actually an MWU activity, an Astro 102 activity, but just show you how easy it is here. This is an H alpha O3 and U, because if you image in red, green, and blue, you saturate. You just can't snap the shutter fast enough with these larger telescopes.
Sure.
So I'll just group them.
Yeah.
Maybe let's color the U band one blue.
Ooh.
Let's bring up the composite here. The O3, we'll color that green. So I'm using narrowband and U band so I don't saturate the telescope. Red, and then I'll come back up here to the percentile mode and hit bright target. So this shows you how easy it is to make a nice picture. Now, astrophotographers, when they do planetary, they have special cameras. They image thousands of, right? We're not trying to do this. These are science grade telescopes, big pixels. But still, there's great lessons that can be learned. If you do this exercise with Saturn, Uranus, and Neptune, they all turn out the right color, which is a nice confirmation of what they're learning in class.
So does each student get an account where they can access these tools, or is it just an open web browser go kind of thing?
It's part of their WebAssign package. Once they sign up for WebAssign, I grab their email addresses, run the script, and they get their own Skynet account preloaded with 1,800 credits, which is like each credit's like a second on a 16-inch telescope at Tololo. So like 30 minutes of time. And it's more than enough for this curriculum and for some playing. Absolutely. And many of them go off and do color images, even though it's not part of the curriculum.
Very cool.
That shows you how easy it is, though. In the second curriculum, we get into advanced stuff like luminance filters, narrowband, and kind of what I had up there at the beginning, complicated layers, building in near and mid-infrared, because it's astrophotography, the multi-wavelength universe. But anyway, Astro 101. How about I show you, I showed you how to measure the distance between a planet and a moon.
Right.
So they can do this for a variety of objects. And we have these plotting tools that we've built, little applications. And before the meeting, I did Triton going around Neptune.
Yeah.
So I'll just grab that data and throw in the Julian dates and the angular separations. They measure right out of that afterglow environment. And it's kind of like a Chi by eye. Yeah. I'll show you how easy it is to get an orbit here.
Very good.
Let's see if I can nail this thing.
Very good. And I think JWC just put out an image this morning of
that's right,
Neptune's rings. So good.
Yeah. And so what you're plotting here, and they fill in the axis labels. That's part of the lesson in the title. But that's separation versus time. This is almost face on. It never crosses the planet. So it gets farther, closer, farther, closer. But semi-major axis, period. And so they can do a little conversion, some ratio astronomy, and they get the mass of the central body. And that's Kepler third activity. We do a parallax activity, which is kind of cool. You need a global network for this. So they image a main belt asteroid simultaneously from northern and southern hemisphere telescopes.
Sure.
So let's take a look at this. Is one I put in just the other day. I was teaching. We train our educators, by the way. If anyone wants to do this, every fall we have weekly 1-hour meetings, and there's a training program. We save them on YouTube in case you're off semester. This is Juno, and here this one was taken in. Let's just check in Cerro Tololo. This one was taken at a telescope called Triple RT in Virginia, the University of Virginia telescope. So I haven't done this forever. Let's see if I remember how to do it. They both have WCS, so I should just be able to align them. So let's select these two images to align.
Okay.
The two Junos. They're taken simultaneously within 2 seconds of each other.
Okay.
And I'll pick, maybe it doesn't matter which one is the reference image. I'll submit, and hopefully they overlap. It's going to crop it to the overlapping region. Okay. And that's the one. And did I select them both?
I
I
thought
did.
yes.
Well, let's, I don't know. And maybe let's just keep going, see what happens.
Yeah. Keep going.
I'm going to stack them now, the two Junos.
Okay. Stack, stack.
Average, no rejection.
Do.
Okay, Juno stack. Here it is. And let me adjust the brightness and contrast. Yeah, it worked. So I just went to, we have kind of these presets. You can tune them if you want to see more things, right?
Sure.
But I'll just go here. This is clearly the asteroid.
Nice.
And so we can do our measuring tool.
Yep.
I'll just do the centroid this, centroid that. And here it is, 8.3 arc seconds, and they work through the calculation.
Very
And
cool.
we don't get detailed into the trigonometry. We assume it's perpendicular to the baseline, but
Sure.
they can get the distance to the main belt.
Cool. So how many students do you have in a typical given year, and then roughly sum total?
Across the now 30 institutions, it's about 3,500 students, and it's growing. 2 years ago, it was 1,000. So it's growing rapidly, and this is because the NSF support.
Nice.
And we have plenty of telescope time for this.
Cool. We'll put some links to this in the description below the video. People can get it.
Great. I'll show you one more from Astro 101. What is this? This is an RLIRE. And so I'm not going to load in all the images, but basically you load in all the images, you photometer the RLIRE, you photometer a reference star. I'll show you a photometry example in a little bit. But it does photometry. It has fancy photometry, it has basic photometry. You can, all the algorithms are professional quality. You could publish it. And we're very interested in that boundary between student experiences and publication. That's probably where we're going to go next. But let me just demo this. Actually, I'll go to the beta site because it's a little bit better. And I'll upload a demo file here. Afterglow photometry. No, that's not it. Upload. This is demo files. Here we go. Okay. So you pick your variable star. It's this one. The other was a reference star. Now it subtracted them. You can type in magnitude of the reference star. I'm not sure what it is, but you get the idea.
14.
Add labels and everything. And then we have Lom-Scargill periodograms built in.
Oh, very nice.
Like Fourier transforms, but for non-uniform data. To give them a hint, right? So this thing's about 0.33. You go to period folding. And we made some changes here because period folding was kind of a black box. And so you can actually see the period folding in process.
I love that.
And let me slide it down to close to the right answer so we don't have to wait too long.
Yeah.
And I'll period fold down to the 0.33. Actually, let's put on 2 cycles because that's kind of traditional with this field.
Yes.
And there it is. Okay.
Beautiful. Beautiful.
So you know this is an RLIRE, so it's a standard candle, and so they can calculate the distance.
Yeah.
And then in the following lab, we give them a whole bunch. We don't make them analyze each individual one, but and this will probably be the last activity I show you from the 101 curriculum.
Okay.
They can take them all, and I've done this for a bunch, have the data here, and it makes a top-down projection. So here we give them 30 out of the 150 globs out there.
Okay.
And I just pasted that in, and they calculate the distances based on what they just learned. We also do Cepheids to nearby galaxies and things, but here are the distances. Teach them a little Excel, makes the top-down projection, and then it's kind of eye by eye. There's the center of the galaxy.
Nice.
There's the size, so you can show we're not at the center, like Shapley argued. And from the size, they then go take images of the spiral nebulae, measure their angular size, use a Cepheid in them to get the distance, figure their physical size, and see,
this is great. This is great.
And so this is the stuff we teach in 101, but they can't do it in traditional nighttime 3.5 inch.
Right.
The philosophy was they can either learn how to use telescopes,
which is what you get out of that.
In old days, how to struggle with telescopes, or skip all that and get right to the science. And our philosophy is majors should learn how to use telescopes. But these survey students, maybe the last science course they ever take, let's get right to the science.
Exactly.
So we build a foolproof system that's easy enough for them to use.
Very cool. I was going to say, this thing also, you know, in a classroom environment, this also lends itself really well to group projects, to parallel projects. So each person can do a different piece of the puzzle, put us together. So I really like that. It builds the team aspect. Things go in parallel. Very nice.
Yeah, we often have them work in teams, and particularly the 102 curriculum, it is teamwork, because they're eating up a lot more telescope time in the 102 curriculum. And so maybe one person gets the red data, one the green, one the blue, one the luminance, one the H alpha, and so forth.
Cool.
Okay, you want to see some 102 stuff?
Let's see some 102 stuff.
Okay, it's more advanced, as should be the case. So here I have some stellar fields. These are stacks. So in 102, they're getting many images. They're dithering. They're stacking to get rid of defects. There's B, there's I, there's R, there's V. It's an open cluster, NGC 2437. With the planetary nebula is actually just a random foreground object. So in this is module 1. And I have a team of 24 educators fleshing this out.
Oh, wow.
And that's the cool thing about this second curriculum, this second grant. And we have a participant program for this. Educators can join after teaching Opus. They also get, in both of them, there's money for the adopting educators. Okay. But here, they're building the curriculum and I'm building the tools. And so they told me to go build this, and this is what we did. Cool. So let's photometer this field. Okay. Let's figure out the age of this cluster.
Ooh.
Within minutes, just to show you how easy we can get it. So I'll pick one of the bands. Maybe I'll pick the V band.
V band.
And I'll go to photometry. And, you know, you can do things like photometer, single source, and it goes and it hits, and in a moment, it'll pop up an aperture and annulus. Showing that it's done, but I'm just going to get rid of that. And we are going to photometer everything in the field. So we're going to extract the sources. Takes a moment. So there are like 2,000 to 3,000 stars in this field. And all the extraction settings, they're a little bit more technical, and photometry settings, they're up here. But the defaults are usually good enough that students don't need to worry. So it's found them all. It's going through, and it's already calculated the 0 point. Because in my settings, I tied this to AAS. Okay. Now it's going through, and for each star, it's calculating photometry. Wow. But if I go to another field like the R band here, gets a little slow with that many points on there, but here's the R band. See, the sources are already found here. Yeah. So while it's doing the photometry for individual images, I'm going to have it set up to photometer. Let me go to the bottom of the list here. The V, the R, the I, and the B. Okay. Okay. All right. And I'm gonna photometer it. And this will take probably 1 or 2 minutes. Just think, 2,500 stars per image, 4 images, 10,000 stars. You're gonna photometer 10,000 stars on your video podcast. And so you worry, is this going to eat up 15 minutes? But it won't. It won't be that bad. Very cool. Okay. And it will create a download file that will upload into a really cool tool that the educators had me build. So it's now finished the photometry. It's organizing the file, which actually takes longer than the photometry. How about that? And while it's loading it, I'm just going to get rid of the stars. See, the point of this lab is to date these clusters, but then, here it is. Let's download that file. Okay. Go back to the graphing tool. Let's go to Cluster Pro. Ooh. They kept adding stuff in here, the educators. Okay. You know, there are HR diagrams in your textbook, in the student's textbook, and then there are HR diagrams that you publish, and they don't look anything alike. And so how do we bridge that gap? And so this was our attempt to do that.
Mm-hmm.
So let's load in the data we just collected.
Okay.
Download, here it is. Okay, and there are a lot of stars, so this will take a second. Okay, here it is. And we can always see that this, so we started by plotting HR diagrams, V, V, V. Let's do R, I, R. So you get two different HR diagrams, and I can label them here if I want, B minus V, and I'll save you all that. And it's an open cluster, so there are a lot of field stars. You can see the cluster here because the professor said with the open clusters, it's hard to see what's going on. Cross-correlate with Gaia when you load that in.
There you go.
Okay, and so it's Gaia cross-correlated. And you can see, if I zoom out, all the field stars there. And so I'm going to center this up. It's a little laggy because there is a lot of data in the browser right now, but I'm going to get the crosshairs kind of close to the center. Okay. And then I'm going to clip around it, getting rid of everything but those.
There you go.
Okay, now I'm looking pretty much at cluster stars.
Oh, that's looking great.
And it's Gaia, so I can turn on a distance clip.
Yeah.
That's concerned is about 30%. And so let's find the distance to this cluster. Too low, it's right around there. Okay.
Uh-huh.
Now
the tricky part.
We gotta, all the blue stars are gone.
And so this the black line here is
an isochrone.
Thank you.
Yep. And so it's a model for stars that all formed at the same time. Mm-hmm. What it should look like on the HR diagram. Yep. There's a little bit of reddening here, so I'm going to slide that up a little bit. And let's see, maybe a little less metallicity and a little bit younger. And you get the idea. You could play with it a little bit. The stars should ride on the isochrone in a perfect world.
Right.
Because the binaries.
Measure the age based on main sequence turnoff, yeah?
Yeah. Mm-hmm. And what I've learned, you get the main sequence turn off, and with globs, it's hard to get down to the main sequence, but you can pick off the horizontal branch and still get an age.
Fair enough.
Yeah, you can fiddle with it and get it really perfect, but you get the idea. What I say, log age 4.8, 8.45, dust 0.17, really crude. Here's WebDA 8.39, dust 0.15. So, if I played with a little bit more, I could get a little closer.
Very cool.
Okay, so that's one of the MW Astro 102 activities. Want to see another? Want to collect some data? I
do.
Okay, let's go to Skynet. I haven't shown you Skynet yet.
Oh yeah, let's look at that. There we go.
Let's do something on the radio. Let's first see the radio telescope sitting idle. We're lucky. Let's snag it. Now we're building a whole new interface. This funded by DoD, and it's pretty remarkable. It has like half a stellarium built into it. It's fantastic. But currently our radio telescope's hacked into an optical system. The new Skynet is going to be built optical and radio. Nice. But let's add a new radio observation. Let's do a pulsar.
Okay.
PSR, my favorite's 0329 plus 54. It's the brightest, easiest.
That's why it's your favorite.
It's right on the horizon, and there are mountains there. This is Green Bank, so I'll be looking at a mountain. I gotta pick another pulsar. How about 0950? Oops, 50 plus 08. That's another good one. Right now, it's getting ready to set. Let's go for it though. Let's try. I'm going to lower the horizon just down to 0, and going to grab this thing. Okay. Going to submit. The filter's fine as is.
Wow.
And let's just, we're going to track it just for a minute.
So each image is a credit, or a credit is number of seconds?
A credit is number of seconds. Now here in the radio, this is a 1 pixel camera. So we're just measuring a light curve essentially. Brightness is a function of time.
Yep.
And let me submit it because it takes about 20 seconds to take. Wow. Go back to Skynet Live and see when it takes.
Wow.
Okay, it just took a minute initializing. We can actually track it. We have webcams on most of the optical telescopes, but you can't put a webcam on a radio telescope because webcams make radio noise. So we have this kind of tracking thing.
Wow.
Right now, you have a 6-story, 150-ton telescope in West Virginia moving because we press buttons. Imagine students pressing buttons and this happening. I'm still going for the webcam like a mile away on a telephoto lens because it'd be so awesome to watch this thing move. Let's see. Where's my target? It's over here somewhere.
Yeah.
I passed something that was bright. Well, I passed right by the sun. See that right there?
That's kind of bright.
Yeah. Okay. And so I think I've settled. Okay, the receiver is setting. We have 2 polarization channels. This is live read from the 2 polarization channels.
Wow.
It's doing a calibration measurement right now. That's a fake signal it sends through the receiver. It goes through all the same electronics, so you can calibrate because from day to day, the oomph that comes out changes, right?
Yeah.
And
weather.
We refurbished this with in 2009 with Stimulus Act money. And so it's a nice system, helium closed loop cooled. It's good.
Very cool.
And it's collecting data. I don't see any spikes, but this one, it's fainter. The spikes might be in the noise.
Okay.
But the tool we built should pull it out. Actually, we'll let it finish. I did collect it a few minutes ago, a few hours ago. So we can go straight and analyze it. So let's go to the Pulsar interface. I'll just grab the identical data I pulled down.
Those interfaces. Whoa. Wild.
Let's see this right here. So once you pull it down, now you can see some spikes.
Yeah.
Listen to this. When I didn't share, I'm going to stop sharing.
Sonify.
And I'm going to reshare, and there's a button, share sound.
Yeah, I was going to say, I saw that.
Okay, and I'll sonify. You can't really hear it in there. Maybe it's in there. So let's go and do the same period folding. We have a periodogram.
Yes.
And it's cranking. Okay. Let's maybe shrink it down a little bit. We don't have enough resolution here.
Okay.
Range 0 to 0.5 seconds. There it is.
Bang.
Around 0.25 seconds.
Wow.
And actually, it's sensitive to 4 decimal places, so I should read more carefully. 0.253. Actually, let's zoom in. 0.25, 0.255. Compute. Make sure I
got that centered. There you go.
0.2530. Period folding 0.2530.
Yeah. Pat.
I'll just tune it to see if I can make it any higher. That was a little higher, a little lower. Okay, so right around there. Now sonify it.
Oh yeah.
It's been binned and down the noise. Now, if you have a really bright one, I'll bring in my favorite 0329.
Okay.
Demo files, this one, 0329. It's strong, really strong. And I should know its period by heart, but I've forgotten it. Somewhere between 0.7 and 0.73.
Okay. Ta-da.
0.7145. 0.7145.
Okay.
Now, the 2 channels are opposite polarizations. This is the introductory exercise to non-thermal emission. So if I show the difference left over, and you got to calibrate the 2 channels. You do that by looking at something like the moon that's not polarized. But it doesn't matter what the calibration is. I cannot null out that difference.
Right.
So what's going on? The pulsar is sweeping by. The first magnetic field line's curved like this. The second side like that, and so you get a polarization difference. So it's not thermal, and it leads them into discussion of curvature, radiation, synchrotron, and then we start doing radio imaging, which we haven't built yet, but I'll pause.
This is totally awesome. This is totally awesome. I love the idea of putting this kind of technology out into both the intro and slightly more advanced courses. This is really nice. I'm thinking of all kinds of ideas now that because I'm going to be reshooting my course this summer, yeah, this coming May, June, so 23, I'll be redoing, and I am seriously going to consider adopting some of these exercises to do. I think these are awesome.
Back to the HR diagram one. Let's take those images, stack them, color them blue, color them red, color green. Hello. My mouse is, here we go. Mouse is color green.
Sure.
Hello.
Thinking
okay.
There we go.
Yeah, again, a little bit of lag here. And so that's a basic RGB combination. But here is calibrating to actual photometric catalogs.
Yeah.
So that's my blue filter. That's my green. It's my red. We measured the amount of extinction here. I think it's, Webb said it was 0.154.
Okay.
Because we can take out the reddening. And astrophotographers, when they combine an image, it may come out really red first because of dust. And what they do is they change the definition of white. Yeah. And that doesn't work for us. We need consistent color so we can interpret color. So we built in extinction curves. There we go. I'll pick a reference layer and calibrate it. Wow. And so now we have the true colors. I'll go to kind of a better scaling and hit the default so we don't blow out the centers of the stars. And isn't that pretty? That is beautiful. And so they learn for clusters of this age, these are the colors. You bring up something like bluey glob, you get a much older age and you get redder colors. Much redder. Right. And one of the coolest things about this image, look at the planetary nebula. In the middle, you have a faint blue star. Yes, you do. And none of the other faint stars are blue. They're all red like they're supposed to be. Only the bright stars are blue, being a young cluster. Right. But this is a faint blue star because it's a white dwarf. It's a WD. Yeah. Very nice. And so we then go on, and I won't go into details, but in later lessons, we teach them about color combination with luminance filters, with narrowband filters. And so they can put together things like this, where this has not just the color. I'll take out 2 layers, 3 layers. So here's your color combination with luminance. I'm with you. Here's some H alpha to boost it a little bit. Yeah. But here's Weiss 12 micron, which shows warm dust. Boom. And and it's amazing. See how it gives it a 3-dimensional feel? You see where these stars are warming the dust. And here is K-band, 2-mass K-band showing you where all the hidden stars are. So all sorts of great lessons built into these things. Galaxies, where it's not just H alpha, but that's warm dust. Recently, we were playing with the helix. Actually, this morning, there's not enough signal to noise here yet. But if I turn off the infrared bands, you get something kind of standard. Yeah. But there's the warm dust, and here's cooler dust. Yeah. Oh, there we go. Yeah. Yeah. So I like it a lot. Very cool. So how long? When did you start this software? Is this like the end product after 2 weeks, or you've been working on this for 2 years? 2 years, or is it 20 years? For a long time. We started building the software in 2005, initially just to control our telescopes for gamma ray burst follow-up. Then we built a new system for student use, and there was an earlier version of this that was flash-based, and so we've evolved to this new platform. It was actually funded through AUI Well, through NSF, but a grant to Tim Spuck at AUI
Okay.
with a focus on accessibility.
Right.
This is highly accessible. There are all sorts of accessibility shortcuts, and there's a sonification region. I can take images, not the color images, but let me just take an image like this, and I can sonify it. And so think of a keyboard going across the bottom, and it will play notes as it hits them.
Love it.
Boom, boom, higher frequency. And so we're working with blind visually impaired students, deaf and hard of hearing students,
right,
on different accessibility aspects.
Cool.
That's Kate Meredith at Glass.
Cool.
So, yeah, we've been building it a long time. As the money comes in, we keep adding new things. The color combo is newest.
So what is the what are some of the future ambitions that educators would like to see added to this?
So we're working really hard on the astrophotography, and we're almost there. The goal is to get to 85% the quality of an APOD with 15% of the learning curve. That's our motto.
85% for 15% of the work. There you go.
The astrophotographers, it's a huge learning curve for Photoshop, PixInsight, all these programs. Some of them you have to pay for. This is free once you have your Skynet access. You actually don't need Skynet access. AUI has a version of this where you can create pure Afterglow accounts and just upload information of your own. Yeah. And after that, the big add will be the radio. We've built these amazing algorithms. There's a 50-page paper on FJSUP where we've built, right, if you wanted to make a picture on the radio, use an interferometer. Very, very few people use single dish. So we're kind of like the expert of single dish mapping.
Yeah.
We're expert in something no one does. Very few do. GBT does it a little bit. And we've built in these great tools for RFI removal, because RFI is everywhere and it's going to confuse the students.
Absolutely.
Here's a great example. This is a 40-foot teaching radio telescope. It's cool with fans, right? It's not it's not cool with closed loop liquid helium or anything. And you're rastering up and down because it's a 1-pixel camera, and it's picking up on the one polarization channel the transmitter from Roanoke Airport's bouncing off the ground, polarizing, going into this channel. So all these blips is RFI. You may think it's totally ruined, but we've built these spatial recognition algorithms because I know what the shape of something that's been diffraction limited is, and you get this. And here's the other channel that's not contaminated, so you can see how close you can get. And so we have this whole suite ready to go, and we're going to integrate it into the version 2 of Skynet that's coming out hopefully sometime this year.
This year, coming in.
Okay. Yeah. Those are the immediate goals.
Very cool. Okay. And what's been your experience using it in the classroom?
It's been, I just stopped sharing. Though, like, system updates are popping up. Are you sure you want to close it?
No, not now.
Close it. I don't want to update my system right now. The experience, so we have an education research team. With these large grants, we're able to get the best. And it's mostly Australian based. David McKinnon, who's an old hand at this, he in terms of statistical analysis, he's the best. I mean, I used to do surveys and think I was learning stuff. No, there's so many tests and hoops you have to jump over before a survey is validated and believable.
Yes.
And so we got him. We got Michael Fitzgerald, who runs the Robotic Telescope Science Research Education, Student Research Education Journal and Symposium. There's student Rachel Freed and a whole bunch. We have a whole team. Tim spoke. And they're doing amazing work. We now have from Opus 2 years of surveys. And they're looking at attitude, self-efficacy, career intention, content knowledge, those sorts of things. They focused on self-efficacy for starters, because everyone thinks about learning gains, content knowledge gains. But I think people have focused on that over the years because it's the easiest thing to measure.
Low-hanging fruit. Yeah.
And yeah, and if it's a survey course, is that really the most important thing? Does it really matter if they remember Jupiter's composition 10 years from now?
No,
It does matter if they left with a good attitude about STEM.
that matters.
Self-efficacy matters.
Got it.
Self-efficacy
Got it.
is confidence. And if they feel they can do this, they may become a STEM major. If you want to produce STEM majors, self-efficacy is the big thing. So we focused on self-efficacy first. And they do all the careful analysis. They've been publishing in PR, they're doing great work. And let me try to relate in just a moment the finding so far. And so they have this thing called effect size. It's like the number of sigma you move your class from the pre to post test.
Okay. Mm-hmm.
Pre-survey and a post-survey. A before survey, after survey. They call it pre-occasion, post-occasion. It took me a while to get their lingo. And 0 to 0.3 sigma is negligible. 0.3 to 0.7 is moderate. 0.7 to 1 is large.
Okay.
Large is like mastery learning. You master a topic before going on to the next. Okay. 2 is like one-on-one tutoring, right?
Okay.
The goal has always been, can you achieve something in the 1 to 2 range in a mass-produced classroom kind of environment?
Yes.
Self-efficacy, we're achieving high 1s and even 2s and sometimes 3s.
Oh, congratulations. That's awesome.
So they're walking away believing I can do this. But the best part, in the pre-occasion, there's a gap between the guys and the girls. It's well known, the gender confidence gap. And by the end, there's no difference. And so the Opus curriculum, the introductory one, we haven't tested the other one yet. It's removing the gender confidence gap. So we're really excited. The education research is proving fruitful.
Yeah, that is super. Yeah, and I'll get to your point. In a lot of these intro courses, they're not going to be astronomers.
Yep.
As they go on. But it's an educated citizenry, and some of them will become legislators of one thing or another, and to have them look back and have a really positive experience with that intro course, that is huge. It's amazing.
Yeah, that matters. Yeah, I view it twofold. The people who never come back, we got to boost their attitudes.
Correct.
And the people who might come back or might not even know that they might come back, we can boost their self-efficacy. Maybe they'll come back for another course. And the idea behind MWU is to seal the deal. The DoD curriculum is to seal the deal and turn them into majors.
Got it. Particularly on gender issues to put that balance a little better than what it is globally across the field right now. Mm-hmm.
We have ground to make up. Though at UNC Chapel Hill, among our student population, it's about 50-50 after years of this curriculum. So I'm pretty pleased.
Nice.
My favorite, I had a journalism major in one of my 400-seat intro classes, and she liked it. She went on to do my summer program, which the DoD curriculum is based on at Green Bank Observatory. Decided to become a radio astronomer, did an internship, and then went off PhD. And she's discovered, I forget, like 7% of all millisecond pulsars. She got her first one tattooed to her wrist, the folded light curve.
Oh, that's awesome.
Yeah, that's my favorite. You can pull people out of these survey level courses that never realized they wanted or could do STEM.
Could do this. Could do it is a large. You can do this.
And they don't need to go into Astro. God knows, we don't have the positions, right?
No, we don't.
But that first astronomy course is a gateway to chemistry, physics, geophysics, data science, engineering, so many things.
Computer science.
Can we make more STEM majors in general? And that's what DoD wants to know.
Very nice. I think you got an A+ going so far. And I wish you many more happy grants to keep this going.
Thank you.
Either that or some private funding will drop from the sky and you'll be good for a while.
Yeah, that'd be nice too.
Very cool. Dan, I want to thank you so much for spending some time talking about this wonderful set of tools that people can, and instructors can use and students can use in their classrooms right now, today, get the real night sky. It's very cool.
Thank you. It was a pleasure. And if anyone out there is interested, just email introastro at unc.edu. It will go to me and I'll get you on your way.
And we will put that link in the description below the video and make it even easier so you don't have to remember it, and it'll be really good. Very cool. Thank you so much, Dan. And
thanks for having me.
I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
All right. See ya. Bye.